In this problem, we have this automobile, which is on this 10-degree incline. We're given the weight of the automobile is 3,500 pounds. We're told that the initial velocity this automobile is traveling at is 20 feet per second, and the coefficient of kinetic friction between the ground and the wheel is 0.5. So we're interested in figuring out how far will this car skid if the driver jams on the brakes. So what's this distance? This distance S right here that the car will travel. And a couple of things we should note. We should note our initial velocity is equal to 20 feet per second. And our final velocity is going to be equal to 0 because we want to figure out how far will our car skid before it comes to rest. Now, I want to use the principle of work and energy for this problem, and the principle of work and energy says that our initial kinetic energy plus the sum of the work of the forces on our system is equal to our final kinetic energy. And our kinetic energy is going to be equal to 1/2 times our mass times our velocity squared. So if we look at this for our system, we know that our initial kinetic energy is going to be 1/2 times our mass times our initial velocity. I think I called it V naught squared, plus the sum of whatever forces, the work of whatever forces are on our system, and it's going to be equal to 0. There is no final kinetic energy. Our final kinetic energy is equal to 0 because our final velocity is equal to 0. So since our velocity is equal to 0, this entire term is a multiplication term. Our final kinetic energy is equal to 0. Now, how do we figure out the forces that do work on our system? Well, the easiest way is to draw a free body diagram. And to draw a free body diagram, we're going to identify all of our forces, and then we're going to identify which forces do work and which forces don't do work, if there's any forces that don't. So we know this car has a weight, and this weight is going to be acting directly down. And its weight right here is going to be equal to 3,500 pounds. We know this car slams on its brake, so its tires are not rotating, and the frictional force of the road is going to be acting in this direction. Since our tires aren't rotating, our frictional force opposes our direction of motion, and our car is moving down the ramp, so this is the way the frictional force works. And our frictional force is equal to our coefficient of kinetic friction, which is 0.5, times our normal force. So we need a normal force. And our normal force, we're just going to say is right here. We're going to treat this as as a particle, and our normal force acts perpendicular to the ramp that it's on. So which forces do work? Well, weight does work if it has a displacement in the y direction. Since here's the car right here, and at the final position our car is right here. So there is this difference in the y direction. And this right here is going to be the height change that we need to figure out what it is. So our weight does do work. So we're going to have to account for the work of the weight. So let's just write that right now. The work of the weight. And our frictional force. Well, our frictional force also does work. So let's write down, we're going to have to account for our frictional force. Now, what about our normal force? Well, our normal force is always going to be perpendicular to our direction of motion. So regardless of where we are on the ramp, our normal force is going to be perpendicular to it. So our normal force is not going to do any work on our system. because the any perpendicular force does no work, and perpendicular to the direction of motion. So we don't need to account for the normal force. So let's look at this weight force. We know that the equation for a weight force is going to be minus the weight times the change in height, and this is going to be equal to minus the 3,500 pounds that this car weighs times the change in height. Well, it's going to start, the change in height is going to be going down. It's going to start at this position. It's going to end in this position. So this distance right here, if we know that our car moves a distance of s feet, this distance right here is going to be s times the sine of this 10 degrees, because this becomes our s. This is still a 10 degree slope right here, so it's going to be s times the sine of 10. Now the only other thing we need to account for is this is going to do a positive work. Why? Because our weight is moving down. So this is our final position, and our final position is lower than our initial position. So this is really changing a minus. The change in y is really a negative number. So that negative number right here is going to cancel out with this negative work right here, and it's going to create some positive work. So this is going to be equal to 3,500 times s times the sine of 10. And that's simply because the final position is lower than our initial position, so our change of s is a negative. Now, what's the work of this frictional force? Well, the work of this frictional force is going to be equal to, it's a constant force, so we know the equation for a constant force is F times the cosine of theta times the distance this force does work on. And if we call this our 0 point right here, we know that this is a distance of s, so the total distance that this frictional force does work over is just this distance of s. Now, this frictional force is completely in the opposite direction of the motion. So this cosine of theta right here goes away because it's not a frictional force that's projected on an angle or anything. So the frictional force is just in the opposite direction of motion. They're opposite but same. They lie in the same sort of. Our motion is moving like this, and our frictional force is just against it, and there's no angle between these. So our frictional force is going to be minus this mu k na times s. And we can figure out what this normal force is, right? So if we create a coordinate system that looks like this, and here's x and here's y, and we sum our forces in the y direction, and we know this is going to be equal to the mass times an acceleration in the y direction in Newton's second law. We know that there is no acceleration going this way. The acceleration is only in the x direction. So the sum of our forces in the y direction is equal to 0. Positive this way. So we know this angle right here is 10 degrees. So the sum of the forces in our y direction is going to be this minus weight, which is minus 3,500 times the cosine of 10 plus our normal force. And this is equal to 0. So our normal force right here is going to be equal to 3,446.8 pounds. we can plug this right here into this equation right here. We know what our coefficient of kinetic friction is. It's 0.5. So we get our work done by our frictional force is equal to minus 0.5 times this 3,446.8 times this distance that the car skids. So now we have this part of the equation. We have this part of the equation already. So let's just, I guess I forgot to fill it in, so let's just fill in everything now. We have this 1/2 times our mass, and our mass is going to be our weight divided by gravity. So 3,500 divided by 32.2, because we're in English units, times our initial velocity. Our initial velocity is 20 feet per second. So 20 squared, plus our work. So the work of our weight is 3,500 times S times the sine of 10. I'm running out of room, so I'm just going to go down to the next line right here. So to be continued, minus this frictional force right here, which is minus 0.5 times 3,446.8 times S, and this is going to be equal to 0. Okay, so we have this entire equation, and the only unknown we have is this S. So we can solve this equation for S right here, and we get S is equal to 19.5 feet. So what is this saying? What's this saying? This is saying that when we slam on our brakes, if we're moving at 20 feet per second on this 10-degree incline, we're going to skid for 19.5 feet before we come to a stop.